Okay, Cup. Welcome to this will be the 8th class of emerging technologies for lifelong learning. In the previous 2 classes, we had the privilege, the honor of inviting Professor Honyak to give us a very insightful introduction to nanotechnology and the wider implication vis-a-vis how sustainable or not sustainable future, your educational journey, and so forth. So we were quite fortunate and quite privileged to have that 2 lecture. Okay, and today could be, I guess, probably one of the most exciting topic you will possibly encounter in your undergraduate. But I'm only able to give you like a glimpse or a initial taste of what the subject is all about. And that subject is the subject of quantum computing. Okay, so let me give you a little bit of let's call setting. Okay, now quantum mechanics and quantum field theory, let's say quantum physics as a whole, is beyond, way beyond what we're going to be able to cover in this class, and it underlines pretty much a modern society. Okay, it's everything you touch here and there, trace in terms of technology, in terms of what makes your life easier. It doesn't matter if you're talking about cell phone or I don't care, transistor, computer, whatever. Ultimately, traces its foundation one way or the other to quantum physics. Okay, but we're not talking about quantum physics in general. We're talking about quantum computing. Now, as the word say, it has quantum in it, so that's quantum physics, and this computing. So it's a, your intuition would be that it's applying quantum technique, so to speak, to computing, and you would be right. You would be right. But as you see, that it requires a whole lot of rethinking about what it means to do computing. Okay, so in fact, computing is not doing things with the computer that you see. Okay, the reason computing equates to what you do with your computer is because that's the computational paradigm that the technology allows you to do. Okay, so the technology allows you to have this thing called digital computer that you have in front of you. And so when you say computing, it's doing everything on this kind of computer. Okay, but computing as a general concept is not defined to just, it's not restricted to just doing things on this kind of computer. Okay, so obviously we'll be talking about a different kind of computing machine. And not only is it different, it does different kind of computing. Okay, so that's what you have in mind. So in other words, it's not turbocharging the computer, make it quicker and faster. Okay, that's not what quantum computing is all about. Right. Today I will start fairly slowly, but I will actually try to do 2 things today. Okay, one is, remember that in our plan, this class is going to give you a schema for thinking about things. Sorry, it's going to give you a framework for analyzing technology, and it gives you a little bit of library of different technology set that you can look at. Now, let me add a little bit of schema today. Okay, and it's I guess what I call the big 5 and the small 2. Okay, in other words, there are altogether 7 terms here. Okay, 7 terms here: art, mathematics, science. Let's just add S just to be safe. Sciences, engineering, technology, invention, and innovation. Okay. Now, arts is usually not really confused with the rest, but it is actually a big part of the educational journey that we try to give you here. But for the purpose of today, okay, for the purpose of today, I want to highlight this thing, the big four: mathematics, science, engineering, technology. You can think of it as some kind of lineage, okay? Maybe something like mathematics is the mother of science, and science is the mother of engineering, and engineering gives birth to technology, okay? And the two things that we are really interested in as a curriculum is the notion of integrated innovation. Now that falls under this thing here, innovation. Invention, well, invention is like coming up with entirely original thing, okay? And that is something that to this day is not something that can be taught in school. It's sort of like a personal integration of everything you learn and your awareness of the problem and the needs of the society or whatever you decide to do, the solution you're trying to solve, and you come up with invention. So you can think of invention as some kind of internal integration of your knowledge, whereas innovation is more like external integration of all the. So let me put that down. Invention is sort of like a personal or internal integration, integrative process. Okay. Whereas innovation is more of is what we're trying to instill in you guys. Okay. It's external. It's even societal, you can actually say. In fact, when you work with a team, that is a society of sort, right? Okay. And when I say societal, I don't mean like social network. When it's a community of knowledge, right? When I ask you to do literature survey, see what other people have done on previous attempt to solve a particular problem you're interested in solving. Okay, literature survey, technology survey, finding out what the frontier area is. That's the societal bit. Okay, so anyway, today is a very good day, not only to talk about quantum computing, but you can't really understand quantum computing without understanding classical computing. And classical computing is a brilliant, brilliant, brilliant example of how you have all these elements traced together. Okay, so some innovation, you can say something like some innovation, so like pops up almost readily from mathematics. Things like cryptography, right? Once you get the mathematics right, it's almost you invent the encryption. But computing is a whole slew of things, I think. Now, to make cryptography practical, yeah, you need everything else. You know, computer engineering. You need the data transmission, the internet or computer-to-computer protocol and whatnot. But certainly, you can say almost as sort of like a eureka moment. Once you discover the math, you immediately invented cryptography. Okay. Now, to say the whole computing ecology, it takes everything from math, science, engineering, technology. I don't know if I can say in equal measure, but it's a long story. It's a long arc that covers all of this. Okay. So keep this in mind, and I'm just going to say, you know, arts. When you talk about art, you think aesthetics. You're driven by something that is inherently beautiful. Okay, there's another philosophy that say science, good mathematics, in a way can be guided by beauty. You can think of a lot of area where, you know, we talk about this in the during the nanotechnology lectures, that sometimes aesthetic principle like symmetry drives the discovery. You know, the double helix, the benzene molecule that's driven by, thinking about symmetry, the 6-fold symmetry of the benzene molecule and so forth, and the double helix and so forth. So there's a whole bunch of, there's a big area of how people think that aesthetics almost subconsciously drives mathematics and scientific discovery. Okay, but we're not going to talk into that. We're not going to talk about that. So mathematics, when you talk about mathematics, you have to think of axiom. In other words, mathematics does not get started until you establish some kind of axiom, some kind of truth that is that's agreed upon. It's like if you're going to play a board game, okay, you can't just have everybody come in and start playing a board game without explaining the rule. So think of axiom as a sort of like the basic fundamental first rule of whatever mathematics. Now, there are different branches of mathematics. What it means is that there are different kind of axioms, just like there are different kind of board games you can play, right? If you want to play the mathematics game of topology, you have one set of axiom that you definitely have to obey. You want to play the mathematics game of probability, then you have the axiom of probability and measure theory that you have to obey. You can't break this, okay? Because you're not playing the right game. Okay. So once you have the axiom, everything that flows from axiom, unless you're committing logical error, must be true. Okay, it is inherently true by the truth established by the axiom. To be disrespectful, you can say it's a little bit like shooting fish in a barrel. Okay, the truth is in the barrel, the fish is in the barrel, so you can't miss. But that's being very disrespectful to mathematics. But my point is that the truth is established from get-go. You don't have to discover, you don't have to test. Okay, the truth is derived. Once you have the axiom that 1 + 1 = 2, and 1 + 2 is the same thing as 2 + 1, everything else is true. Okay. Now, if the axiom doesn't apply, then certainly this is a matter of application. 1 + 2 is not necessarily the same thing as 2 + 1 in some application, right? If you take well, the funny anecdote would be the English, right? The English are actually fighting to this day. Well, it's not, they're not really fighting as to how to make the right tea, right? Do you take tea? Do you add milk? Or do you actually pour milk in the cup and do you add tea? So 1 + 2 and 2 + 1 to this day are not equal in the eyes of the English when it comes to, adding milk to tea, tea to milk, and vice versa. You have the camp that say you definitely have to have the tea in the cup and then add milk, and then you have the entire camp that say you have to have the milk in the cup and then you add tea, right? So that's 1 + 2 is not equal to 2 + 1. Okay. So with science, it's different. Truth is not so much established from axiom as much as it is discovered. So you have to discover something. Okay. Now, as a prelude to the class today, I'm going to add a little bit about the bit of mathematics and science that is going to be important. Okay, in mathematics, it's binary logic. Okay, binary logic or logical operator. Okay, I'm just going to add that. Just throw that right there. We'll use it later. Okay, science, think of discovery. And you can think of, I'm going to be referring to this later. So send me. Okay. Okay. Now, engineering is about making sure that whatever you want to do is practical. Okay, you can make a computer that can add 2 numbers, but it takes you, 5,000 baht to add 2 numbers. That would not be practical. So usually you can think of practical in terms of cost, in terms of manufacturing, in terms of market readiness, whatever. Okay, and then technology, you can think of confluence. And in fact, a market readiness would fall mostly under confluence. So things have to come together. The people have to be educated, there has to be some kind of the right societal moment that adopts this technology and so forth, right? So this is where mathematics, science, technology. Let me say one more thing. The confluence is not only of the people and the market, but it's also the different engineering. For example, for the computer engineer, for the integrated circuit to be viable, and for you to be able to have this cheap computer with chips made in Taiwan. By the way, most critical chips are made in Taiwan, not in China. You would need not only the technology in terms of the computer architecture, but you certainly need the technology of manufacturing, of having clean room and whatnot. It's a whole bunch of things that has to be mature at the same time. So think of confluence as things being mature at the same time, or by the time you want to make the technology happen. Okay, so ingredients have to be ready. If you need 5 ingredients, all 5 have to be technologically mature. Okay, otherwise you don't get the whole technology set. Okay, now the small 2, and that's a whole education. This is a whole of Basai basically. Okay? You are inheriting the art, the mathematics, the science, the engineering, the technology, almost from most of this from other departments within July, for example, right? But you make it happen over here. Okay, so this is a good schema of thinking about things. And if I were to be somewhat unkind, I can make an essay exam that asks you to describe the art, the mathematics, the science, the engineering, the technology, the innovation, the invention of nanotechnology, and which elements of nanotechnology is mathematics, which elements of nanotechnology is science, and so forth. And same thing with blockchain. I can say, okay, I throw you the word blockchain. What is the art of blockchain? What's the mathematics of blockchain? What's the science behind it? What's the engineering behind it? Technology? What's all this? So all these 7 items, if you can identify components, okay, then you are gold. You're good, because you will realize then that this is the bit that you don't know. You need your friends from engineering department. This is the bit that even your friends in engineering department can't help you, because it has to be discovered. This is the bit that maybe you need some understanding, but you can sort of like have an intuition on it. This is where your design thinking, your creative thinking comes into play, but your role is right here. Okay, so if I take a whole concept of nanotechnology, and which bit is art, which bit is mathematics, then you are responsible for the innovation bit. That's who you are. Okay, so think of it this way. It's like assigning a division of labor, as it were, but it's an intellectual labor. Okay, so you have 7 friends, an artist, a mathematician, a scientist, an engineer, and technologist, a really good tinkerer and inventor, and you. This is you. This is you. Okay, so you take nanotechnology, you separate into 7 bits, and you drive this bit, and you let your 6 other friends do the other bits. Okay, so this is a good schema that I want to party with, and it's actually the last schema that I'm going to give you for this course. Okay, but it's a good timing, because I'm going to be referring to this when we talk about classical computing versus quantum computing. Okay, so let's take that as a good preamble. Took a little bit longer than I wanted, but okay. First of all, again, you guys know that as I mentioned many lectures ago, I don't always like, I use slides, PowerPoint slides to make business presentation. I don't necessarily like it to use it to teach, because again, it's very linear way of thinking. But in this case, trust me, quantum computing is not a linear story. Okay, in fact, I'll show you. There's this a very good YouTube called Map of Quantum Computing. you will see that once this guy has drawn out the map, quantum computing, it's a very nonlinear story. It's a very nonlinear story. Okay. Nonetheless, I'm going to give you a linear narrative, sort of like beginning to end, like the world before quantum computing and the world after, and so forth. Okay. And so you have these slides. I gave it to you on the Zoom, on the line group chat. Okay. Now this talk, I have to tell you, it's not a new talk. This is a talk that I've given. This was 2018, I believe it was 2018, October 2018. Yeah. So back when I was doing the quantitative models and enterprise analytics, I was heading that program at Siam Commercial Bank. We had a very kind of interesting day, okay, of talk called disruptive technology. So, you know, what's going to disrupt the banking and the business and so forth. And so there were, you know, 3 or 4 main speakers, right? One, I think, in maybe nanotechnology, one in blockchain slash digital currency, and so forth. And I was the one giving the talk on quantum computing. Now, so the theme of that day was, what is the emerging technology that's going to disrupt your business in general, banking in particular? Okay, again, the theme of the day was, what kind of emerging technology will disrupt you, okay, as a business owner, or you as a banker or financial professional? So that was the theme of the whole day. And the way I frame the thinking was that you have disruptive technologies, okay? Like nanotechnology is disruptive technology, blockchain is disruptive technology, but quantum computing has the potential to disrupt those disruptive technologies. So, you know, that's why I want you to stare at the title page a little bit longer. So quantum computing not as a disruptive technology necessarily, although it is certainly, it is actually the disruptive that disrupts other disruptive technologies. So quantum computing as disruptive technologies, disruptive technology. So that was the claim that I made at the beginning of the talk. Okay, and there have been some technological progress in the last 4 years, but what I'm going to talk about today hasn't changed. Okay, hasn't changed. The fundamental truth I'm going to be, and again, this is an introduction class. Okay, right. Okay, so once again, and I'm going to have this little chart ready to refer back periodically, right? Okay, so let me move that so like to here. Okay, there. Okay, let's put that there. Good. Okay. Like I said, you can't really, I'm going to actually be giving you an introductory talk on quantum computing, but it's almost impossible to do without actually giving you the whole classical computing story first. Okay, because what you take for granted as classical computing has its own why, what, when, and how. Okay, so classical computing, all right, classical computing is a discipline. Think of discipline as an area of study. Okay, it involves science and engineering. So again, we talked about here, science and engineering. Okay, involved in using binary digits. Okay, manipulation via logic gates. Okay, so binary digits, manipulation via logic gates. This is all mathematics. Okay, implemented mostly on silicon semiconductor. Right now is you don't have any kind of other kind of computer. This is what you have, semiconductor. So it relies on this technology. this science and also technology here, to perform general purpose information processing. Okay? And by the confluence, I mean there's a science of semiconducting, and there's a science and the mathematics of what it means to do computing, and there's an engineering of putting all things together and so forth. Okay. So science and engineering discipline. Okay. The whole science and engineering of classical computing is about using this thing. This is the fundamental object, the most fundamental thing you have, the ultimate building block. Okay, like the ultimate building block of life is RNA or DNA. This is the ultimate building block of computing. It's a binary digit. Okay, it's things that can go 1 or 0 and attached to another things that can go 1 or 0, attached to another thing that can go 1 or 0. So you have strings of 1 and 0. Okay, that could be manipulated. So it's not fixed forever. It could be manipulated. 1 turns into 0, 0 turns into 1, depending on some mathematical logic. Okay, and this is conceptual, right? 1 and 0 is conceptual. Well, you have to make a physical realization of 1 and 0, and that's where semiconducting circuit comes in. Basically, if you think of conducting, what does conducting mean? Conducting means it's conducting electricity. It allows electron to flow. Now, something that's conducting allows electron to flow. Something that does not conduct does not allow electron to go. So it's a closed door versus an open door. Okay. Well, semiconductor is a thing that closes at times, open at times, depending on how you configure it or how you implement. Okay. So conducting means open channel. Non-conducting means no path, no way through. Semiconductor means it's a door. It can open, it can close. Okay, and you have a mechanism for controlling whether or not it opens or closes. Well, if you equate opens to 1, close to 0, or if you equate close to 0, open to 1, then that opening and closing represent binary digits. And the mechanism for turning 1 into 0, 0 into 1, and vice versa, and all kind of manipulation is the logic gate. Yeah. So that's a whole bit here. Okay, that's the whole science of engineering. Now, it's not there just for fun. It serves a purpose. So this purpose is information processing. Okay, literally, it's just information processing, because information gets translated into zeros and one, and when you manipulate zeros and one, that's like processing. Okay, so you have something that start out with 1 1 1 1. After processing, it's end up with 0 1 1 0. Okay, that's what it means. Okay, except 1 1 1 1 has to mean something, hence it's information. When you turn 1 1 1 1 into 0 1 1 0, you're doing some processing on it. Okay, now if you're doing just that, it's not very interesting, right? Well, what you happen to have is a hierarchy of programs, functions upon functions upon functions upon functions. Okay, so first of all, the first hierarchy of function is to turn this 0 and 1 1 0 into operation that can add 2 numbers, right? Then you can have add hierarchy of function. Well, how can you turn addition into multiplication? Well, how can you turn multiplication into integration? Well, how can you turn that into manipulating computer screen? All the way until you get your computer games. Okay, so it's a hierarchy of computer program. Okay, that does all this. Okay, which is not available in mechanical. I just add that because historically there were actually such thing as mechanical computing. So that's what classical computing is. Okay, classical computing begins and ends with binary digits. Okay, binary digits is just strings of zeros and one. How you manipulate it depends on the mathematics of logic gates. Then you turn this into electronic component. You turn logic gate into electronic operations. And then you have the basic of computers. And then you have functions upon functions, upon functions, upon functions, upon functions, to the extent where the computer can now have artificial intelligence. Okay, right. So that's classical computing. We've been doing pretty well so far. Okay, so let's move to quantum computing. Let's go with what quantum computing is not. You see, you notice? Okay, let's. I might as well do this. Sorry. Okay, quantum computing is not. It's not. What is it not? It's not old paradigm on new substrate. What I mean is that it's not doing exactly the same thing here, except, you know, instead of doing it on semiconductor circuitry, you would do it on some kind of magic substance. Okay, so if you're doing exactly everything the same here, okay, but the substrate, the sort of like the physical realization, you take away semiconductor circuit and you add some kind of magic material from space, and you do that. Okay, that's not what quantum computing is. You're not just doing the old things, but instead of on silicon semiconductor circuitry, you're doing it on quantum device. That's not what you are doing. Okay, so let's do that. It's not what you're doing. In fact, let me give you a little interesting history. Okay, there have been plenty other attempts. Okay, not only, you know, not just quantum computing, but to find a new computational paradigm. Okay, now there was I think 10-20 years ago, there was actually an active area what's called DNA computing. Okay, I encourage you to look it up. DNA computing is not about using computer to analyze DNA. No. DNA computing is about taking a pool of DNA. Remember, we have this technology, PCR, that multiplies genetic codes. Well, you can think of those as fundamental strings. Okay, so there was an effort, by the way, by a lot of scientists, enthusiastic scientists and engineers, to try to say, well, what if we put numbers, encode information into strings of DNA, and encode instruction in DNA manipulation, right? Because DNA can cross over and so forth. RNA or DNA, I'm not quite sure, but they call it DNA computing. Okay, and so if you think about it, you have a bunch of numbers, bunch of information that you want to process. You encode that onto the DNA, and have the DNA, you know, crossing over, this kind of mixing of gene and so forth. That is your processing. Once the processing is done, you sort of like decode the DNA that you ended up with, and that's your solution. Okay, so let's see. Let's go to internet for a little bit. Wikipedia, DNA and DNA computing. Yeah, there's that page there. Okay, the area is not dead, but it's not as active. Okay, it's not as active. So literally, you're trying to encode a problem. Let's say your problem is to find a combination of logistics that will minimize transportation cost. Yeah. Last year, your TNA and I, we actually had a project with logistics, you know, mixing and matching different kind of coals into a barge so that it has certain chemical property and minimize the transportation cost or whatever. Okay, so you're trying to find a solution. DNA computing is say, well, let's turn those requirements into DNA and have the DNA mix. And after a few hours, when all the mixing is done, you get the final string that is the best, and then you decode that. And that's your solution. Okay, so that's DNA computing. So that's a kind of an interesting side note. Okay, that's an interesting side note. Well, I want you to think of that. I want you to think of that because in a way, even though this is entirely new substrate, the mathematics is still pretty much the same, right? It's kind of like doing some kind of combination, except instead of having the zeros and one represent in digital, you kind of like have the solution printed on DNA. Okay, maybe it's not binary, it's quaternary because it has four gene values. but roughly speaking, it's kind of digital computer, right? And you're still finding combination. Even that, some would maintain it's still old paradigm. Okay, it's old schooly. Some people say though it's a new paradigm, but I could say that relative to quantum computing, DNA computing, as esoteric as it is still old paradigm. Okay. Now here's what quantum computing is. I'll give you the definition, and then we'll show you how it works, and then we'll see how it's going to disrupt all other technologies. Okay, it's still science and engineering discipline. Okay, but the beginning and the end, the beginning of it all is not ordinary bit, but it is qubits. Okay, well, entangle is, forget the word entangle. It doesn't have to be entangled, but usually involves that. It's quantum mechanical binary. Okay, so this is something else entirely. Okay, and the jury is still out as to what best physical substrate it is. Remember, go back a few slides here. Nobody in the world will disagree with me when I say that digital computing is implemented on silicon semiconductor circuitry. When I say mostly, I mean 99.999%. Okay, the other 0.0001 maybe DNA. Okay, but basically it's decided. This is how the world is. Okay, this binary digit is implemented best, most efficiently, most productively with silicon semiconductor. With quantum bit, we haven't decided yet. With quantum bit, we don't know yet what is the best physical substrate. Okay, some say you use lasers, some say you use plasma. There's, this is still active area of research. Okay, this is active area of research. Okay, but again, so that's the difference. Now, in terms of purpose, it does not perform general purpose information processing. It doesn't. Not yet anyway. Not yet. Not the way it's going. Okay. It's when you are mapping, if you're able to map any kind of number, any kind of quantity into binary digits, and you're mapping any kind of mathematical function into logic gates, into turning 0 into 1, 1 into 0, then you're doing performing a general purpose information processing. Well, quantum computing does not do that. Okay, this is why I say quantum computing is not turbocharging your iPad. Okay, it does not. It does not. Okay, at least for now, it does not. It only performs what's called search and optimization. Okay, so it's a little bit like the example I gave with DNA computing. Okay, anyway, but it takes advantage of what's called quantum superposition, blah blah blah, to achieve parallelism that classical computing cannot. Okay, so it doesn't do everything that classical computing does, but for what it does, which is search and optimization, it has an entirely different level. It's a game-changing technology because it has parallelism that classical computing can only dream of. And we'll talk about what that means. Okay, so compare these two slides. One is to say you start with binary digits, right? And the manipulation of binary digits, you turn quantity, mathematics, numbers, whatever, into binary digits. You turn mathematical operation, any kind of operation, into manipulating the bits via logic gates. And all this is implemented with semiconductor, right? And then it performs general purpose information processing. And because you have these layers and layers of programming, complexity from assembly code all the way to high level language like Python and even higher level language, Mathematica and whatnot, okay, to do things. Well, quantum computing begins with entirely different, begins with what's called qubit, okay? Mathematically, it's called block sphere, but I'll tell you about it later. However, it's implemented. Sometimes use laser, use plasma, use gas, all kind of stuff. Okay, people are working on it. And it doesn't perform general purpose computing. It performs search and optimization for now anyway. Okay, but the advantage it does have over classical computing is that search and optimization, it's a big problem. It's a wide area to cover. Okay, so it has this thing called parallelism. It's a bit like if you go out shopping, right, and your kid, your kid got lost, right, and you have two parents, okay, looking for the kids. What would you do? Would you, in the same department store, you and your wife or you and your husband would both walk together throughout the department store looking for your missing kid, or would you split up? Certainly you split up, right? The husband would go maybe the second floor, the wife would go on the first floor, they split up. That's parallelism, okay? Simultaneous search, okay? Well, that's only dividing into two, right? So you multiply the search capability by 2. Well, this is multiplying the search capability by 2 to the n. So that's a long story short. Okay. Now, let me tell you this. I don't know if you've seen this picture. You've probably seen this picture. This is a picture of quantum computer. It's a real quantum computer in IBM lab somewhere. Okay, and this is another one. I think it's the same one actually. This one is sort of like wraps over that. I'm not quite sure. Okay, so it's huge. It's huge. It's huge. Now your computer. This is what your computer looks like. That's your iPhone, right? There's a computer in here. That's a battery. The computer is actually, I think it's this big. Okay, although that could be memory, I'm not quite sure. Okay, so that's your computer. Now, go back to World War II or just a little bit after. This is what the computer looks like. This computer takes entire room, has less computational capability than your iPhone, obviously. Okay, now quantum computing also takes an entire room. But my point is that even though this thing, okay, in terms of technology, it seems to be at the same stage as that, right? It takes an entire room, this takes an entire room. This thing has less in common, okay, with your iPhone than this iPhone has with that. So this one is a tiny thing, this one is a whole room, this is a whole room. But these two are actually virtually the same thing. These two things, okay? You can say that this has been miniaturized, but this is very much the same thing. This thing, on the other hand, is entirely new animal, okay? Entirely different thing. So it's less in common with your iPhone than your iPhone is to this thing. This one, by the way, is called Z3. It's historically important computer, okay? And there's a lot of quantum word thrown around. Quantum mechanics, okay, has to do with physics. Quantum binarity, that's where we come in. Quantum state, that's important, the fundamental property that we need. Quantum information processing, that's basically quantum computing without physical realization. It's like a mathematical model of computing with quantum bits. Okay, then you have quantum decoherence. These are all relevant. Now, there are other things that don't make sense, right? Quantum mortis, quantum racing, quantum leap, quantum finance. You see this a lot, by the way. These are all nonsense. Okay, these are all words like turbo. We actually have razor blade that can be has turbo prefix or postfix to it. You can't turbocharge a razor blade. Okay, same thing. You can't quantumize investment fund or management or risk management. This is all nonsense, right? This is just vernacular. Okay, but you allow that for example, a Porsche has a fully electric vehicle, but you have a version of it that's called turbo. Now, turbo, you can't turbocharge a battery. It's complete nonsense. So when you have a Porsche Taycan, which is completely electric, but the Taycan turbo is completely nonsense, right? But it is vernacular. So you take the word turbo to mean something extra, spicy or something like that, okay? So Porsche Taycan spicy, but they call it turbo. So turbo means nothing. Well, same here. There's a lot of times you will see quantum used for all kind of stuff. It means nothing. It means nothing. So beware of that. Okay, beware of that. Now, as you know, my undergraduate's in physics and economics. So certainly I did study quantum mechanics. But I have to tell you this though, quantum mechanics it's a very old school quantum physics. How old? It's before World War II. You can say that by World War II, maybe at least by 1950, nobody uses quantum mechanics in physics anymore. They would use what's called quantum field theory. Okay, so at some different formulation, more powerful. Okay, but the quantum phenomenon that I'm going to talk about is the same. It's the same nature we are describing. Okay, now let's go to something a little bit closer to quantum computing, and yet to my mind and to a lot of people, it's not. Okay, how many of you have heard of a quantum computer called D-Wave? Okay, that is quantum computer, but not quantum computing. Okay, it is a computer that uses quantum phenomena. In particular, it's quantum phenomena called quantum annealing, or quantum tunneling. Okay, it uses that, but it's still not entirely new animal. It's not a new computational paradigm. So to me, when we talk about quantum computing, D-Wave doesn't count. D-Wave is a little bit like all of this with extra capability. Okay, it's not this, Okay, to my mind and for most researchers. Well, I can talk about it later, but this is very interesting. It's mathematically, I actually used this technique when I was a PhD student. It's called simulated annealing. Well, annealing is a little bit like this. Okay, imagine that this is your energy surface. This is your energy surface. In other words, if the ball, you roll like a little metal ball, if it's here, it's stable. 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 If it's here, it's not. It's going to fall. If it's here, it's going to fall. If it's here, it's going to fall, right? This is like what you would learn as gradient descent algorithm later. Anyway, you throw in a ball, a metal sphere or something, and it's going to settle here, 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 here. Okay, and that's called minimized energy. Okay, so you can think of it as a cost. Okay, so go to the lowest cost. But certainly this is local. This is best with respect to this. This is best with respect to this. But this is the global best. This is the global best. Okay, this is the global best. Now, what happened is in any kind of solution finding, you start with some kind of initial solution. If you start here, you would get better solution by coming here. But once you get here, you get stuck. It's called local minimum. Okay, local minimum. Can you see my arrow? Not here, looks like now. Okay, can you see my arrow? Okay. Same here. If you start here, you're fortunate because you end up with the global minimum. The point is, what happened when you start here or here, you end up with local minimum. So you're stuck. You want to get here. Well, you can't get down here from there. You actually have to do a jump. So even though you want to minimize your energy, go down, you have to go something that's counterintuitive. You have to go uphill before you can go downhill. Okay. Now, this in simulated annealing, annealing is the word from metallurgy, like when you sort of like ironsmith. Well, this is annealing means sort of like a lower energy state. Okay. Now, in simulated annealing, you simulating this process, this kind of jumpy process. This jumpy process happens when you have heat. That's why when you annealing ironsmith, they would heat things up. You know, you get them. I don't know if you watch like YouTube or online Iron Smith channel, you know, making sword or whatnot. They already got the shape they want, but then they'll heat it up again and they'll cool it down again. Well, this heating up and cooling down is to allow this kind of settling into a lower energy state. Okay. So yeah, you have to heat the iron so that you can pound on it and make a sword out of it. But you know, once you have the shape, you still heat it up again and then cool it down just to do this. Well, this is classically the way you do it. You add heat, so particle jumps, okay, and basically you settle here by jumping over. Well, quantum annealing is about using the quantum effect of tunneling. It actually jumps here without going over. It's kind of a weird thing that quantum mechanics does. Okay, it literally goes from here to here, and that's what quantum computing in the small sense, in the D wave sense is. It's not our sense. Still, it's a very powerful thing. Okay, so maybe you can go to a D wave. So maybe you can do, is D wave a real quantum computer? You say no. Well, some people say yes, but I would say no. Okay, I would say no. Okay. Right. Okay. So now let's get to actual quantum computing. Okay, let's get to actual. Yep.
I have a question on the simulated annealing.
Oh yes, please.
So I was wondering, like, in order for them to have like a thermal jump at a peak level, so basically the peak level just release all the energy and then it's dropped like that.
Yes.
Oh, okay.
Yeah. So actually, you know what? Do this. Go to your kitchen. Right? And open a drawer, right? You would see a basket of utensil, right? It's sort of like in order, but it's kind of messy, right? Now think of that, right? How would you arrange your chopstick and your spoon and your fork into the lowest energy state? The lowest energy state is when everything is kind of like at the bottom, right? At the bottom. And how would it go to the bottom? When it's aligned neatly. Okay, we're not talking entropy, right? We're not about sense of order. We're talking about getting all, you know, if maybe you can look at my hands here, I guess. If you have a chopstick on top of chopstick, you know, it kind of piles up very high, right? And you have spoon and fork and whatnot. Now, lowest energy state is when it's very low. And the only way you can get all the chopstick to come down very low is to line them neatly. Okay. Now, how do you get the chopstick to line neatly below, neatly in order? Well, most people would do what I would do, which is to shake it up. When you shake it up, you give it energy. Temporarily, the chopstick actually float in the air. That's a higher energy state. You don't want that. But by doing that a couple of times, it settled down to a very nice, neat order. So every time you shake a box of chopsticks, you are doing this kind of annealing. You're adding energy so that it ends up in the lowest energy state. Okay? Now, simulated annealing is taking that analogy and turning it into a computational paradigm. The noise it adds is called randomness. Instead of throwing up the chopstick in the air and letting them land, and hopefully you do it a few times and it would line in a nice order, and that's a global energy minimum, you would use random number generator. Okay. So this I used this in, I think, the first year of my PhD. I ended up not using it in my thesis. Okay. Anyway, so in quantum mechanics, if you have this D wave guy, what they did was they actually used quantum property. It's not jumping over, it's not simulated, it's real. It actually goes from here to here with some probability. Okay, that's what quantum machine D wave does, and it does this. It does solve this kind of routing optimization. What you're seeing on screen here is a very difficult problem called traveling salesman. You have to visit all these cities, Okay, these are all the little cities that you have to visit, and you have distance between them. And depending on your routing, you can waste a lot of gas or you can minimize gas. Well, the global minimization is very difficult. In fact, it's probably like an NP-hard problem. Yeah, a problem that's not solvable in polynomial time. But anyway, that's technical. You can only solve it heuristically. Okay, and in fact, when you turn on your iPhone, okay, to find the shortest route to your restaurant, when you do the Google map, okay, when you do the Google map, it's doing this problem heuristically. Okay, it's not doing it optimally, by the way. Well, it could because the combination from you to your restaurant is small. It's not 100 cities. It's only like 5 different traffic lights you can go to. Okay, so the problem is much smaller. So maybe it explore all the route, but the combination of route is 2 to the n. So if you have 100 cities, you can't solve it. Okay, so your iPhone is working from junction to junction, uses other things, but basically it's solving this problem. Okay, but the problem is tiny. The problem that going to the restaurant is tiny. The problem of routing in huge international or maybe domestic but very large supply chain, that's a big problem. So people like me get paid, lots of money to literally solve this problem for logistic companies. Okay, but it's most of the time it's relatively boring. It's not that interesting. Okay, but it's a meaningful application, and you do get paid to do this sort of optimization. Okay, right. So let me get to the meat of the matter. It takes a while. So we'll quantum computing is a big subject, so we might spill over a little bit. Anyway, tell you what, this is the birth of quantum computing. This is a timeline. I'm not gonna go over this in detail, but basically the birth is here, 1981 roughly. 1981. Okay, so all the technology is here, but here 1980 or 1981 is this year that quantum computing as a paradigm, as a thought comes into play. But it relies on a lot of things that happened before. So this thing, EPR, paradox, Bell's inequality, quantum information theory, this thing came before this. But you can mark down 1980, 1981 as the birth of quantum computing as we know it today. EPR is short for Einstein, Podolsky, Rosen, 3 guys. Einstein you've heard of before from last lecture and from everywhere else. Okay, Bell's inequality and blah, blah, blah. This one solved that problem, and this one underlines this. So once you have the birth of the concept, now the concept of quantum computing, now you can probably hear from popular science that quantum computing is going to break your cryptography, it's going to hack into your bank account and so forth. But that's very pedestrian aspiration. The original aspiration is higher than that. Okay, it came from Richard Feynman. Now, Richard Feynman is one of my heroes. He's an amazing human being and very eloquent in his teaching and sense of humor and whatnot. Look him up. Okay, Richard Feynman. But anyway, what he proposed was this. You have this physics of quantum physics, right? Whether quantum mechanics, like I learned in college, or quantum field theory, or all kinds of stuff. Well, that's the quantum physics you want to study. You studied it with math, and you're trying to use computer to help. Okay. What he said was that, well, nature is quantum, is driven by quantum physics, but you're trying to use classical computer to study quantum system. That's not going to cut it. So he thinks you should fight fire with fire. If you want to study quantum nature of nature, you need computational tool that is also quantum in nature, right? So he wants to fight fire with fire. He doesn't want to, bring knives to a gunfight, right? So he doesn't want to solve quantum physics with classical computer. He wants to solve quantum physics with quantum computer. And that is the motivation, okay, to create a computational paradigm and eventually physical realization thereof that is built from the ground up from quantum principle. Okay. And what's quantum principle? And I'll go into that. Okay. So that's beginning of all that. Now, so from that date, okay, from that date, the hardware. So we're talking about quantum computing as, you know, you can say hardware and software. Well, hardware is not even ready, but the information theory is already found in the 70s. The motivation is already found here. Okay, so let's think about some kind of quantum computer and quantum computing and quantum computer programming. Okay, let's find out how can we get quantum computer to work if we had a hardware. Now, all this, you can think of it as a journey of software engineering before hardware arrives. Okay, because it's a little bit hard to get the hardware. We're still not there in terms of hardware. So a lot of this is theoretical and actual breakthrough, a theoretical breakthrough in software side, so to speak. Okay, so you think of this, blah blah blah. Quantum cryptography was invented. Okay, teleportation invented. Okay, by some guy in the lab. Shor's algorithm. This, by the way, is when you hear about quantum computer can break your cryptography. Well, quantum computer, powerful enough, big enough, stable enough, can use Shor's factoring algorithm to break your cryptography. So the algorithm is already there. The software is done. Okay, it's just waiting for hardware. Okay, so Shor's algorithm was before you were born. Okay, now they also realized that not only do you need a relatively big quantum computer, you need what's called quantum error correction. I'll talk about it later and so forth. So all this now, in the last 10 years, this is where you begin to have a real hardware. IBM actually built a hardware quantum computer, but very tiny one, tiny in terms of number of qubits. Okay, and they launched this in 2016. Okay, and in 2018 was when I actually gave this talk. And Q Experience is a very kind gesture by IBM to say that we have a small quantum computer. You can play with it by sending quantum computing instruction, and we will compute it for you. Okay, but you can't send anything complicated. You can only send simple things like, you know, equivalent of adding 2 plus 2. Okay, so they have a new computer. They say, okay, anybody wants to add 2 plus 2? Okay, let me know. Well, in 2018, I think it was on my birthday exactly, I sent in some quantum computing instruction to their lab, and they computed it a few hours later. I think it was set in a queue because everybody wants to play with it. So I actually from my office at SCB sent a quantum computing instruction to IBM lab that literally fed my instruction to a quantum computer, you know, one that looks a little bit like this. I don't know if it's this one exactly. And then compute the result and send it back or posted it. And you'll see that later. Okay. So I actually, you know, you talk about, you know, quantum computer programming. I have done a baby 2 plus 2 version of that. Just for fun, basically. Well, this is probably a little bit outdated. This was Google search count I did just prior to the talk, just to see if the word quantum computing came up. Okay. Anyway, so to understand quantum, okay, again, the title of the talk is Quantum Computing as Disruptive Technology. To understand quantum mechanics, okay, you have to understand that things are funny at the very tiny level. First of all, raise your hand or shout if you know what the word quantum means. Buddy? Quantum is a singular word, right? Well, let's do this for fun.
I think I know, but I'm not
Yeah, what
really
is
sure.
it? Go ahead.
Is it like the amount of energy that minimize the use of that, and then which like minimize the use of energy involved when it has
No,
something to
almost close, very close when you mention the word energy. Energy minimization is physics. Okay, that's what the world tries to minimize energy. When you stand, you try to lie down because you want to minimize energy. When I give you homework, you try to find the easiest way of doing things. That's energy minimization. That's nature. Okay, classical physics also minimize energy. Quantum annealing, all this is energy minimization. What is quantum is that the energy is not infinitely divisible. Just like nature is not infinitely divisible, you go down small enough, you chop steak into half a steak, you chop half steak into little slice, you chop, all the way you get to atom. Okay, once you get to atom, you can't chop it anymore. Well, you can't chop it with ordinary process. So there's a basic fundamental unit. But energy, you used to think of energy as being just some kind of quantity. Okay, think of it as temperature, as some kind of thing. So it has a continuous range of value. What it means is, let me just write this down real quick. Quantum means energy not infinitely divisible. Okay, in fact, energy is multiple of unit, basic unit. Okay, and that basic unit multiple here is nu. It's just a Greek number nu and h. Okay, what it means is that energy is not infinitely divisible. Energy is a multiple of some basic unit. That basic unit is a quantity. Okay, so what it means is that energy comes in quanta. Energy comes in quanta. Okay, it's not perfectly divisible. Okay, and this thing is called Planck's constant, and this is the frequency. Okay, so anyway, so what it means is, so first of all, energy comes in units, in quanta. Okay, in quanta, and this is actually E is equal to h nu. Okay, I'll use V, okay, because the Greek letter nu looks like a V. E is nu is what got Einstein his Nobel Prize. Okay, I gave you the backstory of that already, right? In a very miracle year, Einstein miracle. Okay, in Einstein's miracle year, he publishes a few things. This one was the one that I told you about when we talk about the side effect of bad model, because the Brownian motion became the fundamental model of financial market, and then I led to a whole bunch of the side effect of using the wrong copula and whatnot. So anyway, he wrote this, he wrote this, he wrote this, he wrote this. Okay, this in a way, and in fact, this is a lot more is earth-shattering, but they couldn't give him Nobel Prize for this because it's not provable yet, or something like that, right? But this one was provable. It's called photoelectric effect. Okay, photoelectric effect is like this. If I shine the light on something, okay, it heats up. Okay, it heats up. If I shine more light, you would think the energy would sort of like goes up proportionally. Well, it turns out that you just get more light, but each unit of light, each photon has the same number of energy. So this is it. H nu, this is it. Okay, oops, sorry. H is Planck's constant, and F, okay, you can say F or say F. Okay. Right. So what it means is that light, okay, only come. Let me see if I can draw this for you guys. This is actually one of the most earth-shattering thing. It's like a, it's like a big viral thing in the physics community. Well, if light comes in energy, okay, and energy proportion to frequency, then that means that energy goes up in steps. Okay, so quanta, go back to the question I asked you, what does the word quanta or quantum means in quantum physics? It literally means step. Energy goes up in steps. Okay, energy goes up in step, and that step is dictated by frequency. Okay, frequency, in this case, frequency of light. So you shine light of certain frequency, it gets certain amount of energy. If you shine lights of different energy, you get different amount of energy per photon. Okay, you have more flow if you shine more light, but each packet of light has the same energy, has the same wavelength, has the same everything. Okay, so that's what this means. So what it means is that fundamentally, what else goes in step? Let me ask you a question. What else goes in step? Anybody?
Our learning.
Sorry?
Our learning, like when we first undergrads and then grads.
Yeah. Oh, that's a step. Okay, let's think about what else physically goes in step. In other words, you can't have something in between. Well, let me give you a hint. Okay, any of you play guitar? Any of you play string instrument? Right? Okay. Well, if you play a string instrument, yeah, it looks like this, right? Terrible. Okay, this is a string, right? Now, when you pluck a string, it goes into a wavy, like this, right? So this is a wave. What else? Can you see this? Make it a bit larger. Sorry. Okay. So this is one. This is another one. This is another one. Right? So the frequency goes in step, right? Because it has to be some kind of multiple of the division. Okay? So what else goes? String on a guitar. Okay? So it has wavelength goes in step. Okay? That's why sometimes instead of saying quantum mechanics, is also known as wave mechanics. Okay? Quantum is also known as wave mechanics. Okay? So, why is this important? Is this just an analogy? Is this just an analogy? I'm trying to give you something. No, it's not. Because go to this guy called Schrodinger. describe physics in terms of wave equation. Okay, now for the next 2 minutes, just enjoy the show. Okay, you don't have to think deeply, but let me just show you. Schrödinger equation. Schrödinger's equation is relatively simple if you know calculus, but the implication is amazing. Okay, what he's saying is this. Right. Okay, there it is. Okay, never mind. Just ignore what else is going around. You notice this phi thing? This is a Greek phi. This is x is position, t is time. Okay, so phi is a thing. Like you are a thing. You are a position in time. You are a thing. A thing is position in time. Okay, what this equation say is that the change in time, partial with respect to t, is equal to something like this times second derivative in position plus some energy. Okay, some kind of energy. Okay, so that's the equation. The equation is describing you. You are a thing in position and time. The change in position, second derivative, and the change in time in the first derivative. So that's what partial differential equation looks like in calculus, except, and this is where except comes in, this thing here is not an object. This thing is what's called a wave function. Okay, it's a wave function. Okay, and just enjoy the show. It's saying this. It's saying this. And this is, I'm going to try to draw this the best I can. Okay, and see if this makes sense. If this is you, okay, well, let's just say this is you. Okay, you are out over here. You have a coordinate. It's a point in time. So actually, I don't have to write down anything about you at all. I just say this is you, right? Oops. So this is you. You are a dot. This is you. You're a dot. Now, if you are a dot and I create a barrier, let's say I make this room here. Can you tell me where you are relative to that wall? Are you to the left or to the right of that wall? You're to the left, right? You're to the left, right? Now, what if this, instead of describing you, I describe as a dot, I describe you as a function. Oops. I describe you as a function. Okay, that function is called the wave function. Okay, I describe you as a wave function. Now that function is a wave function, so you can actually go negative if you want. So this is you. Instead of you being a dot, you are a wave. What's important about the wave is that when I square this wave, that's like taking the absolute value, I give you a distribution. Okay, so step one, you not a dot, you are a wave. It's a wave equation. Okay, you are a wave where you are. So where you are is not described by that. Okay, step two. Okay, square that wave and get a distribution of your location. Okay, and that's you. So in this, instead of describing you as a position in time, I describe you as a probability distribution of location in time. Okay, Now, so what does it, so again, let's try. This is very, I mean, you know, I'm trying to give you third year physics in a first year lecture, so it's a bit hard. Quantum means energy is not perfectly divisible. It comes in unit, it comes in step. And the only way it can come in step, you can think of a physical analogy, is wave. Wave come in step. And so let's do this. Let's describe movement or physics, okay, in terms of wave. In order to do that, you or anything, okay, any object, not a dot, now a wave. And then when you square that wave and get distribution of location, say it. Okay, and that is how, voila, you got quantum mechanics. Yeah, the mechanics of movement of location. That's it. That's it. Now, so far the step is interesting, right? It's fun. Okay, so Einstein, through his work that got him a Nobel Prize, say energy comes in quanta, right? Comes in step. What else comes in step? Wave. Okay. Okay. And Schrodinger's equation describes physics in terms of wave function and equation. Okay. And so now you don't look at things the same way. I don't look at you as who you are, where you are at this moment in time. I look at you as a probability distribution of your location. Okay, that's quantum mechanics. Now, let's say you take this as your physical description of nature. This is what happened, okay? And it's scientifically verified experimentally.